All right, this is Unit 2, Lesson 4 of our Pre-Calc 12 curriculum. The unit is called Parent Functions, as in your mom and dad kind of parent, and then the Lesson 4 is called Solving Radical Equations. What we're going to learn in this lesson is kind of a review on how to solve a radical equation. We learned that in Pre-Calc 11, but we're also going to learn what's new is how to solve a radical equation by graphing. So here's two examples. One example. We have the square root of 3x plus 13, and it is equal to x plus 1. So the first thing we're going to do is we're going to square both sides of the equation, because squaring a number, squaring is the inverse operation of square rooting. And so if I square the left side, it gets the 3x plus 13 out of the square root. The right side, we're squaring a binomial, so we'll FOIL that out. And then we see we have an equation in terms of x with an x squared. So I'm going to solve this for 0. So 0 equals x squared minus x minus 12. I see this is factorable, and that allows me to find the two answers. So this will equal 0 when x is positive 4 or when x is negative 3. Now, this is how we solve this kind of a problem in Pre-Calc 11. Notice we do have to check, because we squared both sides of the equation, we do have to check for an extraneous solution. So we plug back in 4, we find that this does work, because the left side and the right side equal. When we plug in negative 3, we find this does not work. On the left, we get 3 times negative 3 plus 13 is 4, and the square root of 4 is 2. However, on the right, if you plug in negative 3 for x, we get negative 3 plus 1, which is negative 2. And 2 does not equal negative 2, so this is actually an extraneous solution, so we throw out negative 3. And 4 is our only answer. Now, we are not going to do any more algebra in this lesson, except maybe one more example. No, not even, because solving radical equations algebraically can be done, and it's not that bad, but we do have to check for extraneous solutions because we square both expressions at some point. But what we're going to find is that solving radical equations by graphing it, not only is it quicker, but it doesn't give you extraneous solutions. So we're going to take this and we're going to chunk it into two expressions. So the left side, we're going to make this a function, and the right side, we're going to make a function. So the left side, we'll say f of x equals the square root of 3x plus 13. And for the right side, we'll say g of x equals x plus 1. So that was the equation split into two functions. What we have here is the left side is the red line and the right side is the blue line. And we see that the red line and the blue line intersect at exactly one point. And that point is, where is it? Right there, 4, 5. The x value is 4, the y value is 5. Connecting that with our algebraic example, x equals 4 is where the two lines intersect, and that is our solution to the problem. 5 was the y value in our graph of the intersection point, and we plugged in 4 on the left and the right side. We found that both equal 5. Also notice that we don't have is the extraneous root of x equals negative 3, which raises the question, where did that negative 3 go on the graph? Well, to find that, what we're going to do is look at, so when we squared both sides, we got this new equation, which has two different expressions. So the first two expressions was a radical and a linear. When we square both sides, the radical turns into a linear. We got y equals mx plus b. And the linear side turned into a quadratic. We got that x squared plus 2x plus 1 is a quadratic. So if we were to graph those two expressions as a function, we're basically putting a new function j of x, which is x squared. And so if we just put f of x into j of x, we're basically squaring this function. If we put g of x into j of x, then we're taking and squaring this function. So if I square f of x, let's get rid of f and g for a moment. If I square f of x, my quadratic turns into this linear. Note the domain restriction. We don't go any further left than negative 4 1/3. And our range restriction, we don't get any less than 0. Okay, so we got that one. The radical turns into linear. The linear equation, when we square it, turns into a quadratic. Okay, and that has the same domain and range as you would expect a quadratic to have. Now, if we look at where does each expression squared intersect, well, they intersect right here, negative 3, comma 4, and that x value of negative 3, that's our extraneous root right there. We go way up here, our other intersection, so our line intersects the parabola twice. The other intersection is x equals 4, and that is our solution for other graph. So what we found is that when we square the function, instead of intersecting a radical and a linear, now we're intersecting a linear line and a quadratic. And this gives us an odd answer of negative 3, which is not on our original. I think I'm rambling at this point, so I'm just going to move on here. Takeaways. We can use the graph. We can graph each side of the equation to solve radical equations. We kind of explored what the extraneous root is on the graph, and yes, we also know that your math teacher had too much fun last week discovering meme generators. Just for kicks. Oh yeah.